Now let's see what would be the direction of this magnetic force acting on the current carrying wire. If the current in the wire is in this direction, and remember that this is the direction of the conventional current. Here positive charges are shown, so it means that the direction towards the right is the direction of the conventional current, and the magnetic field uh, so this is the direction of the conventional current, and this one is the direction of the magnetic field in which this current carrying wire is placed. So how will you determine the direction of the force, the magnetic force acting on this current carrying wire? You can use the right hand rule for that purpose as well, uh, because this is the cross product of L and B. This magnetic force on the current carrying wire includes the cross product of L and B, and if you remember, the direction of the cross product is determined by the simple right hand rule, according to which you curl the fingers of your right hand in the direction in which the first vector is rotated towards the second vector through the smallest possible angle, and then the stretched thumb gives you the direction of the cross product, which in this case is the force, the magnetic force acting on the current carrying wire. So here L is our first vector, B is the second vector. You will rotate L towards B. You will rotate the fingers of your right hand, or curl the fingers of your right hand in the direction of that rotation, and then the stretch thumb will give you the direction of the magnetic force acting on this wire. So let's do it. You are curling the fingers of your right hand in the direction of rotation of the first vector, which is L. Remember, L is this vector, that is the length of this current carrying wire, and its direction is the direction of the current. So this is our vector L. We will rotate it towards B, and will curl the fingers of our right hand in the direction of this rotation. So curl the fingers in the direction in which L is rotated towards B through the smallest possible angle. So this is the smallest possible angle. The stretch thumb is directed upward. So here the force on this current carrying wire will be directed upward when you applied this right hand rule in this case. Curl the fingers as if rotating the vector L into the vector B. The thumb is then in the direction of the force F. So one way to determine the direction of this force on a current carrying wire is to use the simple right hand rule. The other way to determine the direction of the force acting on the current carrying wire is to use the Fleming's left hand rule. Now here you can see the north pole and the south pole of the magnet, and the magnetic field starts from it originates from the negative pole, and it is directed towards the south pole. So this is the direction of B, and this is a current carrying wire which carries the current in this direction. So this is the angle between I and B, or L and B, the vector L and B, and you can see that it is 90 degree in this case, because it is placed perpendicular to the direction of the magnetic field. This current carrying wire is placed perpendicular to the direction of the magnetic field. So let's use the Fleming's left hand rule, in which you will stretch the finger, the first finger, in the direction of B, which is this. So this is the stretched first finger in the direction of B, and you will stretch the middle finger such that it becomes perpendicular to B, and it will indicate in the direction of the current carried by this wire. So it is this direction, so your second or middle finger is in the direction of the current. Then the stretched thumb will give you the direction of the force acting on this current carrying wire. Here in the diagram you can see this is the magnetic force. This is the direction of the current, and this is the direction of the force acting on this current carrying conductor. So applying this rule gives us the direction of the force acting on the current carrying wire. Another rule which we can use to determine the direction of the magnetic force acting on a current carrying wire is the right hand palm rule, and we just discussed it yesterday in the last lecture. If we spread our palm such that the fingers indicate or point in the direction of B, and the thumb is stretched perpendicular to the palm and it indicates the direction of the current in the wire, then the perpendicular or the normal to the palm will give us the direction of the force acting on the current carrying wire, which is carrying current I in this direction and is placed in a magnetic field directed in this direction. So F is perpendicular to the plane of I and B, and the plane of I and B is contained in the palm. So the perpendicular to the palm will give us the direction of the force, or the normal to the palm will give us the direction of the magnetic force acting on this current carrying wire. Now let's consider the magnetic force acting on current carrying wire in three different situations. First of all, we refer to this basic equation which gives you the force on a charge q, the magnetic force on a charge q moving with the velocity v in a magnetic field v, which is at angle theta with v. So this charge, when it moves in time t, it produces a current I, so q is equal to it, and if this charge traverses a length L of a conductor, if the distance traversed by the charge is L, and if the charge is the negative charge, that is electrons, then the electrons move with a drift velocity Vd when certain potential is applied across the ends of the conductor. Then the velocity with which the charge is moving is the drift velocity. The distance which the charges are traversing in time t is L. So time t will be given by L divided by the velocity Vd with which the charges are moving. And if we replace this q in this equation by I into L over Vd, then we will get this thing. We have replaced q by IL over Vd, which we obtained from this equation, and then there is Vd into sine of theta. But here you can see that there are dots in this region which are showing